All right, gang, here we go. This is for Physics, Unit 9, Part 1. This is the second video in Part 1. We're going to be talking about Coulomb's law. All right, so do some math. In the previous video, we talked all about how charges work, positive or negative charges, how they move from one thing to the next, so on and so forth, and kind of more of the qualitative stuff. And then, as we always do in physics, we go from the qualitative stuff to quantitative. And so now we're going to actually do some stuff with numbers and math, so on and so forth. So this formula right here is called Coulomb's law. All right, and so essentially what it allows us to do is calculate the force that exists between two charges. And those savvy physicists, those lifelong learners, okay, will recognize that this guy looks very similar to Newton's law of gravity that we learned last several units ago now. So the force of gravity, remember, was equal to big G times m1 m2 over r squared. So these two look very, very similar to each other. Okay, so it has the same relationship. The force has the same relationship to charge and to distance as it did to mass and distance when we talked about gravity and circular motion and all that. All right, and so forces in newtons, our Kc value, that's Coulomb's constant. We'll talk a little bit, just very, very briefly, how that value was established towards the end of the video. The Q values, Q always means charge in our textbook. They use a lowercase q. If you're out there looking for additional practice problems, sometimes you'll see it as a capital Q. It's just kind of interchangeable. All right, so you just kind of have to pay attention. Remember, our charges are always in coulombs, okay? Always in coulombs. So if you see anything in nanocoulombs, microcoulombs, you need to calculate it, change it into regular old coulombs. All right, and then our R value, that's the distance from center to center. All right, for our spherical charge distribution. So essentially, what we're saying is if we have two charges, all right, and they're, we could say they could be positive or minus. It doesn't matter. The distance between them would be, that R value would be from center to center. So this would be our R value. All right. And this is always in meters. All right. So if you see it in centimeters, nanometers, picometers, something like that, make sure you always convert it to meters. All right. So now some practice problems. All right. It says the electron and proton in a hydrogen atom are separated on average a distance of 5.3 times 10 to the minus 11th meters. Find the magnitude of both the gravitational force and electric force that's acting between them. All right, so we're just, the electric force is the formula we just learned, okay? Gravitational force is the one I referenced earlier. So gravitational force, that's Fg, is equal to big G m1 m2 over r squared. All right, now big G, that was 6.67 times 10 to the minus 11th. All right, m1, all right, so that would be the mass of an electron or proton. It doesn't matter. So in the previous video, we established what those are. You can just Google them. All right, I have them pulled up here. The mass of an electron is, and make sure it's in kilograms, 9.109 times 10 to the minus 31st. All right, and then the mass of a proton would be the other mass, 1.673 times 10 to the minus 27th. All right. And then that's over r squared, and it tells us the distance between those is this value here. So that, and it's already in meters, so we don't have to worry about changing it. So that'd be 5.3 times 10 to the minus 11th, and then that's squared. Now this is that case I explained last video about how you need to make sure you use that e function in your calculator. All right, it's gonna do wonders to making sure you don't screw things up, because this, this stuff's really not that hard. It's just making sure you put things in the right units and plugging and chugging, essentially what we're at. So you just go 6.67 e to the minus 11th, all right, times 9.109 e to the minus 31st, times 1.673 e to the minus 27th, and then divided by 5.3 e to the minus 11th, and then that guy's squared. All right, so you get and we want 2 sig figs because of that distance there. So you get 3.6 times 10 to the minus 47th. 6 times 10 to the minus 47th, and that's newtons. All right, because it's a force. Now we do the same thing for finding the force of electric force. Excuse me. So that's the formula we just learned. So that's Fe. I'm leaving this spot because there's going to be text here in a minute. Spoiler alert. Fe equals Kc times Q1 Q2 over r squared. All right, and the q's are the charges. The k is that new value we learned. That's the 8.99 times 10 to the 9th. Our q1 value here is the charge of an electron. All right, and the charge of an electron is negative 1.60 times 10 to the minus 19th, and the charge of a proton is the opposite of that, so that'd be positive 1.60 times 10 to the minus 19th. All right, and then our value here would be the 5.3 times 10 to the minus 11th, and again, this guy would be squared. All right, so we go 8.99 e to the 9th times negative 1.6 e to the negative 19th times positive 1.6 e to the negative 19th divided by 5.3 e to the negative 11th squared. And you get negative 8.2 times 10 to the minus 8th. Okay, now this is a good time to talk about something that's pretty important. All right, notice that we get this negative sign. Now, in gravity, gravity always attracts, right? There's only one type of mass, so we don't ever have to worry about it. And you know that the Earth pulls down and I pull up on the Earth. Our forces are pulling towards each other, all right? That's how gravity works. It's always an attractive force. But we learned in the last video that electric force cannot act in either direction. It can be a repulsive force or an attractive force. It can go either way. All right, so what we need to make sure that we understand is we have to think about what's being used. All right, so we've got an electron and a proton. An electron is negatively charged. Proton is positively charged. Since they're opposites, they'll be attracted towards one another. And for our force, our electric force, this negative sign really tells us that it's going to be an attractive force. All right, this is an attractive force. Okay, so whenever you calculate your electric force and it's negative, you know that's an attractive force. And that makes sense because we put a negative and a positive in for our Q values right here. All right, you could imagine if we put two negatives in because they were both both negatively charged, you would get a positive value, and then that would tell you they'd repel. If you put two positives in there, again, you'd get a positive value from this equation. All right. Also notice that these values here, the force of gravity is 10 to the negative 47th, and the force due to the electric force is 10 to the negative 8th. So the electric force is like 1,000 times greater than the gravitational force. It's pretty wild, all right? So what this really shows us is the gravitational force is absurdly weak when you compare it to electrical forces, and then even magnetic forces when we get to that next unit. All right, and so that's one of the big mysteries. If you're curious about like what kind of things are the big mysteries that physicists worry about now, that's one of them. Is, well, what the heck is going on? Why is gravity so freaking weak compared to the electric force? All right, here we go. Let's do another one. Should be pretty easy. All right, a balloon is rubbed against a small piece of wool and receives a charge of negative 0.6 microcoulombs. Uh-oh, look, there's that micro. We got to make sure we put it in coulombs, remember. While the wool receives an equal positive charge, assume the charges are located at a single point on each object and they are 3 centimeters apart. Uh-oh, okay. Again, problem. All right, what is the force between the balloon and the wool? All right, so our electric force, Fe, is equal to Kc, and I'm not going to write out that value because it takes too long, times Q1, Q2 over R squared. All right, so our Kc, that's the 8.99 times 10 to the 9th, times our Q1. Well, it says right here, it doesn't really matter which one's Q1 and Q2 because it's multiplied, and multiplication can go either way. So it'd be, we could just do the negative first. It doesn't matter. Negative 0.60, and microcoulombs, well, that means it's times 10 to the minus 6th coulombs, all right, times positive 0.6 times 10 to the minus 6th. coulombs, and then divided by the distance between them. But this is in centimeters, so it becomes in meters. You divide by 100, so it'd be 0.03 squared. All right, and then that's really all there is to it. We just plug everything in. So 8.99. Play along. 8.99 times 10 to the 9th times negative 0.6 e to the negative 6th times 0.6 e to the positive 6th, or still negative 6, but it's positive 0.6 divided by 0.03 squared, and you get negative 0.36. Negative 3.6, excuse me, negative 3.6, and that'd be in newtons. All right, so again, this negative sign implies that it's an attractive force. So the force between them is 3.6 newtons, and it's going to be an attractive force. All right, so it's going to be pulling those two things together. All right. Now, this is where the rubber meets the road, this next little bit here, and this is the idea of superposition. All right, so so far what we've done is we've calculated the electric force between 2-point charges that are just right next to each other. What we want to be able to do is be able to have a system that has more than one point charge, okay, and be able to take those charges and figure out, well, what would their effect be on another charge that we add. All right, so the net force on an object is always equal to the sum, all right, of all the forces from the other objects. All right, so here we've got this system, and there's a lot going on, so let's break it down. We've got Q1 down here and Q2 up here. Q1 is positive, Q2 is negative, and they're 3 meters apart. And these two here, they're bolted down. We're just going to assume that they cannot move, all right? Now here, we take Q3, and this is the guy that can move around, all right? And we need to figure out what is the force, the net force acting on him. And remember, this is also called the resultant, all right? So this is our resultant, is really what we're solving for, okay? And so what we want to think is like, okay, well, we have to think about what are the values, what are the forces that are acting on this Q3, this third charge. Well, from Q1 is positive and Q3 is positive. So since they're both positive, it will have a repulsive force. So Q1 will push away Q3. And so this force right here, this blue arrow and this F3(1), that is our repulsive force. So this guy stands for the force of 3 and 1. Okay, so this is the force that's being applied from 3 and 1, and it gets pushed up and away this way. All right, now Q2 and Q3, the Q2 is negative and Q3 is positive, so that's going to have an attractive force. So it's going to be pulled this way. Now notice, remember, forces are vectors, so in order to find the resultant, we just have to add our vectors together, and we just go tip to tail. So F3(1) goes up here, all right, and F3(2) goes here, all right, and we can take these and add them tip to tails. Here's F3(1), there's the tip of it. We add the tail of F3(2), we just dragged it down here, we put it over here. So this right here is our resultant, this dashed line, okay, all right, and so so if we were going to figure out where our vector would go, it would be, or our resultant, it would do something like this. It would be a little shorter than that, it'd be like that. All right, so we can do that, and all we have to do is just plot everything out, figure out the distance between them and the charges, and figure out the total forces, and then we can use vectors to figure out what the resultant force would be. All right, and they can get kind of complicated, but they're not too bad as long as you just keep following the same steps over time. So let's try this one here. It says two charges, Q1 and Q2, lie on the x-axis. All right, the first charge is at the origin, and the second charge is at x equals 1. All right, so we've got some guy right here, and so we've got guy right there. So this is our Q1, and he's right here at the x-axis. And it says Q1 has a charge of 10 microcoulombs. All right, so we'll say plus 10 microcoulombs. All right, and then it says the second charge is at x equals 1. So we'll put this over here. So this is Q2. All right, this is our Q2, and it says Q2 has a charge of 7.5 microcoulombs. All right, and then it says determine the force on a third charge, Q3, placed at 0.75. All right, so that'd be somewhere like right here. We'll put an X to show that this guy can slide back and forth. He's not bolted down. And so this guy's our Q3, all right, and his is negative 5.0 microcoulombs. All right. So let's just get an idea before we do any math. Let's just get an idea of what forces are acting on this. So this is negatively charged. Our Q3 is negatively charged, and Q1 and Q2 are both positive. So it's going to have attractive forces in both ways. So we're going to have one force. Ooh, that's like the worst straight line I've ever drawn in my entire life. Let's see if I can try again. All right, let's try again. So we're going to have one force, okay, that comes across here. All right, and this would be the force of 3 and 1, okay, because that's the force of 1 and 3. And then we'll have another force that pulls this way, okay, and we don't really know what the magnitudes are, so we don't really know how long they should be, but this would be the force of 2 on 1, okay. So we need to figure out what these two forces are, and then all we have to do is add them together. So it's pretty easy to do. So we just use our formula, that Coulomb's law here. So we have force of 3 and 1. So we have Kc is equal to Q1, Q2 over R squared. All right, so Q1, that's our 10 microcoulombs. So we say 10.0, and it's micro, so we say 10 to the minus 6th. And then Q2, or sorry, not Q2, we want Q3 because that's our other charge, and that would be our negative 5.0 times 10 to the minus 6th. And then the distance between them, well, from 3 to 1, through 1's at 0 and 3's at 0.75. That's what it says right here. So the distance between them is 0.75, and then that would be squared. All right, and then let's go ahead and set up the other one before we pick up our calculators, because nobody likes to pick it up twice. So we want the force between 2 and 3. All right, so that'd be Kc, all right, is equal, and we need the charge on 2. So that'd be our 7.5 times 10 to the minus 6th. All right, and then we need our Q3 again, which is still negative 5.0 times 10 to the minus 6th. All right, and then the distance between them, well, from 3 to 2, 1 to 2 is 1, and 1 to 3 is 0.75, so 3 to 2 would just be 0.25. 0.25, and so this guy would be squared. All right, so our Kc value would be 8.99 e to the 9th times 10 e to the negative 6th times negative 5 e to the negative 6th divided by 0.75 squared. All right, and so we get, round for 2 sig figs, we get negative 0.80 and newtons. All right, again, so negative sign means that it's attractive. So that means the F31 is 0.80 pulling that way. All right, that same arrow that we predicted. And then F23, all right, so we take our 8.99 e to the 9th times 7.5 e to the negative 6th times negative 5 e to the negative 6th divided by 0.25 squared. And we get 2 sig figs, so this would become negative 5.4 newtons. Now again, all right, again, this is an attractive force, so that means this guy right here would be 5.4 newtons pulling to the right. So our arrows are a little backwards here. The one to the right is pulling way harder, and it has way more force pulling on it. And it's primarily because of that distance, right? It's a lot closer. It's 3 times closer than to 2 than it is to 1. All right. So in order to figure out the total distance, our resultant force, all right, total on 3, all right, 3 total, or total 3, we just take these two guys, and so we take our 5.4 minus our 0.8, and we get 4.6 newtons. So that would be the resultant force acting on Q3, which is exactly what we got. And it goes to the right. And it would be important to say this as well, so we'll go ahead and, oh, I guess my face is blocking. This would be 4.6 newtons to the right. All right, that's what we got right there. Okay, last thing here, electric force. So we've already hit on these as we've worked through these problems here. It says electric force works a lot like gravity. It's a field force. Okay, and we'll talk about what that means in the next video. All right, now the similarities, okay, they're both forces that are related to distance in the exact same way. The farther away you are, the less your force is effective. All right, now the big difference is that your electric force depends on having two different charges, negative and positive. If they're the same, then they attract, and if they're the same, they repel, and if they're different, they attract. All right. Whereas gravity, it doesn't matter; they're all the same. All masses are the same, so they're always going to pull towards each other. So electric force, you have to keep track of. Well, is it repelling or is it attracting? And then the other thing you have to keep track of is your electric forces are always far stronger than your gravitational forces. All right. So these are the big takeaways right here. All right, this guy here, this is Coulomb's apparatus. All right, and so Coulomb, this is how he developed his balance. He used a torsion balance, kind of like this one right here, and so he's got this balance here that's hanging from a wire. All right, and then he charged this sphere right here, and then he brought in another charged object. And so essentially what you do is you let this guy come to rest, so he's not going to move at all. Then you introduce this other charged object. And based on this ruler that's on the outside, you can measure how much does this guy turn based off of the charges on those two objects. And based on those ratios of the charges and the distance they move, you can figure out, well, how much force was applied. And so he knew the tension on this wire, and so he used these twisting of the wires in order to help them calculate that. Pretty ingenious move, and very, very similar, if you remember, how we calculated, we talked about way back when we talked about circular motion and the big G, right? Very, very similar. They used a torsion balance there as well to calculate the big G. So that's it for the end of part 1. Lots of fun stuff we've done so far in this unit. Do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.